Just you say u belongs to x1 such that x is equal to what? EU. Correct. And now we have to prove E is a left identity for RE. Okay, so we calculate EX. It should come as X. So E into U, it is what? E square U, it is EU, it is what? EU is what? X. So we have proved. It implies that E is left identity for RE. Similarly, we can prove E is a right identity for LE. So I left this to all of you for this. All of you can do this. Okay, so we move to next definition. Next definition is that an element A dash in semigroup S is said to be inverse of A in semigroup S if A dash A is equal to A and A dash A is equal into A dash is equal to A dash. If these two properties holds, A dash is equal to A and A dash A is into A dash is equal to A dash, then we say that A dash is the inverse of A. Correct. Now remark is that every regular element has at least one inverse. Write down as a fact. Every regular element in semigroup has at least one inverse. Correct. Say, proof. Let A belongs to S is regular, correct? Then there exists X belonging to S such that A is equal to what? AXA, correct? Now let B is equal to XAX. Correct. Now we show that B is the inverse of A and B is the inverse of A. Then you calculate A, B, A and B, A, B. Calculate this. This is what? A, X, A, X into A. This is what? A, X, A, X, A. This will come as A, correct? Now BAB means XAXA, XAX. So AXA is what? A. So it will come as X A XAX. Now this is what? XAX. So this is what? B. So in this way we have proved that every regular element has at least one inverse. It may possible it may have more than one inverse. It's not like group. In groups every element has unique inverse, but in regular semigroup element may have more than one inverse. That is, for example, it may possible that for example, B and C are the inverses of A. Then what happens? A equal to ABA and BAB is equal to A. And A is equal to ACA and CAC is equal to A. So it's not like groups that element have unique inverses. No. In regular semigroup, element may have more than one inverse. Inverse is not unique. But at least it has one inverse. We have proved. And one example is that if you take example of rectangular band, then every element is inverse of any other element. Now one more fact is that for any element A in a regular D class, any inverse of A dash of A also lies in D. Means element and its inverse are D related to each other. We will prove this. For any element A in a regular D class, any inverse A dash of A for any element A in a regular D class, any inverse A dash of A also lies in D. Correct? So we have we know that all of you can see that what we have A dash A, and A dash is equal to A dash A dash. We have this, correct? So and also we can write like this: A dash is equal to and A dash A. So see, what are the implications from this? You can see that you are multiplying A dash A by left and you are getting A, correct? And also A dash A, when you multiplied A by something by left, you are getting A dash A. It means that from these we are getting four things: A, L, A dash A, and A R, A dash, and A dash L, A dash L, A dash, and A dash R, A dash A. So from these implications, we can see that all this happens. A L A R A dash and A dash L A dash. Okay. So we can see all these things that A and A dash A are related to each other. We can see from here. Is it true or not? See how we are multiplying. You see, we are multiplying A by, from the left side we are multiplying A dash. You can see that A and A dash A are related to each other. How see this is A dash A, isn't it? We are multiplying A by left and we are getting A dash A, correct? And also A dash is multiplying by left and we are getting A. So in this way A, L, A dash A are related to each other. If you see this, how A, R, A dash, see, when you multiply A by right side by something, you are getting A dash, and when you multiply A dash by right side, you are getting A. So in this way A, R, A dash. Now you see how A dash and A dash are related to each other. You see, when we are multiplying a dash by something, we are getting a dash, correct? And when we are multiplying a dash by something, we are getting a dash. So in this way, a dash, a dash are related to each other. And now you see, when you are multiplying a dash by something by right, you are getting a dash a. And when you are multiplying a dash a by right, you are getting a dash. So in this way, a dash or a dash a are related to each other. Now from here we can see a dash and a dash, these are common. What does it imply? It implies that a R composition L a dash, that is D, that is a D a dash. So it means that inverse and element and its inverse are related to each other. This we have to prove. So we have proved it. But remember all these: a L a dash a R a dash, a dash L a dash, a dash R a dash a. All of this should be memorized. We will use all these things. That is why I am telling you. So now we move to theorem 2.3.5. I'm writing here a L a dash a R a dash a L a dash a dash. Theorem 2.3.5. Let A be an element of a regular D class T in a semigroup S. See, what is first we will do the first part, correct? Let A be an element of our regular D class in a semigroup. It means we have a regular D class. So it's, if A is regular, it's every element is regular, correct? Now first part is what if A dash is the inverse of A, then A dash belongs to D, and we have already proved this, isn't it? That A, D, A dash, they are D related to each other. So we have already proved this, correct? So what we have to prove more? Two H classes RA intersection LA dash and LA intersection RA dash contains idempotent A dash and A dash A. Well, we know that A dash and A dash A both are idempotent, isn't it? As we have seen, AX and XA are what? Idempotents. So they are also idempotent. All of you can check it. A dash into A dash will again come A dash A, and A dash A will again come A dash A. So they are idempotents, no problem. And it is also very trivial that A dash belongs to R intersection LA. From here you can see A dash and A dash, A dash, A R A dash. So from here you can see A dash belongs to RA, and from here A dash belongs to LA dash. So A dash belongs to RA, A dash belongs to LA. So it implies what? A dash belongs to RA intersection LA dash, correct? So in this way, similarly we can prove A dash A is belongs to L intersection R dash, and we can also draw it like this. This is A, this is A dash, correct? This is LA, this is RA, this is LA dash, this is RA dash. So A dash will be here, and A dash belongs to RA intersection LA dash, and here A dash A. A dash A. A dash belongs to RA dash intersection. A dash A belongs to RA dash intersection LA. RA dash intersection LA, isn't it? So it is clear. The first part is trivial. All of you can do. Now we do the second part. Second part, if B belongs to D is such that RA intersection LB and LA intersection RB contains an idempotent E, F respectively. And then HB contains an inverse A star of A. Such that A star is equal to E and A star A is equal to F. So see, so what is the question? If B is in D such that R intersection LB and LA intersection RB contains idempotent E and F. Is it clear? Means, for example, this is A, R, and this is B. So what is this? If it is B, it is LB, and and this is what? RB, and it is what? This H class is what? LA intersection RB, and this H class is what? LB intersection RA. This is the H class, correct? Now what they are saying, R intersection LB contains an idempotent E, and L intersection idempotent contains F. Now they are saying that, okay, now they are saying that if it is so, then HB means LB intersection RB. This is what? HB, LB intersection RB. It contains an inverse A star of A. Here there exists some inverse. We have to find inverse here, A star here in this cell. So A star is HB contains A star. We have to show that A star is in HB such that A star is equal to E and A star A is equal to F. We have to prove this, correct? So basically we have to search an A star, and we have to search that A star. That A star should be in HB, and A star should be related to RB, as well as A star should be related. A star should be R related to B, and A star should be L related to B. Then only we can say A star is in HB, correct? First we have to search that A star which is H related to B, and after that we will show that A star is E and A star